And I will announce later on this afternoon, I'll send out an email. I'm going to have some extra office hours tomorrow. That seems to be the best. Tuesdays and Thursdays seem to be the only days that you can break free at all. So I'll be in tomorrow afternoon. Email to come later today. And just one last reminder here. There's been a number of cadets are missing classes for whatever reasons, athletics or so on. Major Cone's done all this effort to videotape, so they are out there and available for you to review. If you miss a class, that's a good opportunity. And plus, I need a lot more hits, guys. My sons are making fun of me. So, tell your friends, just get lots of views going, all right? I'd like it up around 1 million by next week if you could. But on a more serious vein, occasionally I am, we are looking for your impressions, feedback, and how you find these. It's a lot of effort to do it, so it would be nice for us to know how it's being used, received, and the value, all right? Today we're going to continue with Bayes, which we've seen is just another way of looking at conditional probabilities. A key thought we talked about using the Monty problem was a posterior probability, updating a probability based on information we've received. And then when we cut through all the formula, came back to it, it's just really nothing more than a contingency table using it in a different way. So today we're going to do some more examples. I'll go through a contingency table again, but now I'm going to show you 2 other ways to look at this, and it will culminate in a probability tree. Now I personally don't care. You have 3 ways to solve the problems that I'm going to give you in the quiz and the test. You can use the Bayes formula, you can create a contingency table, or you can create a probability tree. And I won't require either one, but I've found in the past that some cadets like probability trees, and it works really well for them. Most tend to like contingency tables, but I want you to see all of them because there's pluses and minuses to each technique. Okay. So let's start with a clean slate here, a new example. Let's suppose that I've analyzed my problem and I've come up with this contingency table. My states are working with cadets again, M and not M, male and female, and in-state and out-of-state, I and I complement. And let's just suppose that out of 200 cadets, this is my distribution, and by now you can quickly answer questions in probability from a contingency table. For example, what's the probability if I select a cadet that will be male? 94? 184. Or 184 over 200, right? What's the probability if I randomly select one of these 200 cadets, that cadet will be female in state? 200. And then the conditional probability is the one I gave here, P of I given M. Well, how would you say that in an English sentence then? Translate from the notation back to a sentence. Dinah? Right here, that notation, translate that back into an English sentence in the context of this problem.
Knowing the amount of males, which ones are in sleep?
Right here, P of I given M.
So, given the amount of males, given the amount of males, the probability of them in state.
Yeah, given a male, what's the probability that a cadet is also in state? Okay. So that is my contingency table, and I think you're getting pretty comfortable working those. Now I'm going to make a little change to this, and all I'm going to do is divide all the cells by 200 to get decimals that are really representing probabilities. Because another way to look at this table is a table of probabilities. sometimes it's easier to think of things in whole numbers, and you can imagine, all right, there's 10 female cadets, I can get that in my mind. Well, it's just as valid to divide by 200 and view all of these as decimals or probabilities. So there's the 92% that are males, the 8% that are females, the 42% that are out of state, and 58% that are in state. Trust me, I just took all the numbers in the previous table, divided each by 200. And obviously I get a 1 there. And I'll just have you note that you can still calculate conditional probabilities here. You're just working with a ratio of probabilities and a ratio of, usually integers. What's P of I given M? The same question that I asked in the previous slide. Well, I'm given M as 0.92, and I divide by 0.53, then I, and now I get 0.58, same number as I got before. Right? The only difference is I've normalized this set of table, which I constructed for convenience, that made it easy for me to understand. Now I've translated it back into a table of probabilities. Clear? Now a little bit of terminology. The probabilities in red on the outside we often call marginal probabilities. So and inside the numbers in the cells, I put the notation for what that probability represents. That's P of M, probability of a male, probability of female. Out of state, in state. So the red numbers are called the marginal probabilities. Makes sense, they're out in the margins of my table, aren't they? The ones in the middle, the blue ones, are called the joint probabilities. And they're joint because it's the probability of two things happening. It's the probability that I select a male who's in state or a female who's out of state. Okay. Joint probabilities, joint marginal. And you notice what's missing there? What's one kind of probability that's not showing up in that table? My conditional, right? Wouldn't it be nice if I had a way to show all of these probabilities at once? I could see the marginals, I could see the conditionals, I could see the joints. And guess what? That's called a probability tree. A probability tree is just an arrangement of all these probabilities, and it's in a certain order, an order that makes calculation easier. And I ordered according to this equation we all know and love by now. P of A times P of B given A is P of A and B. Now that'll make sense in a minute when I show you the tree, but that's the rationale for arranging my nodes or leaves on the probability tree. I'm going to start here, I'm going to go to there, and I'm going to end up there. This is just an alternate method to calculate probabilities. Got some pros, it's got some cons. The idea is we'll fill in nodes in this tree using information in the problem statement. Just like in a contingency table, we'd pick a nice number, say 10,000, 100,000, then we'd back into values for the other cells. And when we did that, we found it pretty easy and intuitive to calculate the probabilities. Well, you could take that same information from the word problem and pluck values directly right into the nodes of the tree. You wouldn't have to construct a probability contingency table. And if you're comfortable with working with this probability tree, it might even save some work, more direct step. And the idea is I will have filled in many of the nodes of this tree, then using either this formula or some basic rules, I can fill in the rest of the nodes. All right, so let's see what a probability tree looks like. And this is a tree where I'm starting with the event A. I could just as well start with B, but I'm going to start with event A. What can happen? Well, I either get A or not A. Pretty obvious, right? Those are marginal probabilities, aren't they? They were out on the margin of my contingency table. given that I have not A, what are the two possibilities? I could get B, or I could get B complement. Right? Nothing controversial. And given that I have A, I can either have B complement or B. See the pattern? I'm starting out with it's A or it's a complement. Then what else could happen? Well, if I've got A, I could either then get B or B complement. And now here at the end of the tree, I have the joint probabilities. Why did I put them there? Because this times this equals this. It's ranged according to that formula. No accident. Let's do an example. If you went back to the contingency table we just looked at and mapped every probability there onto this tree, this is what you'd have. You'd have your marginals, P of M and P of M bar, and you'd have all your joint probabilities over here. What's missing? I don't have my conditionals, do I? How do I get the conditionals? Well, go ahead.
The last one divided by the first one?
Yeah, it's easy. Oh, on my tree, I know I would get this number by multiplying this one times this one. That's the sequence left to right. So if I want that marginal probability, I just divide this by this, and I get the marginal. I'm done. Making sense? You can tell from the expressions. So I did that calculation, and those would be the marginals. 0.05 times divided by 0.08 is 0.63, or you could read it from left to right. 0.08 times 0.63 is 0.05. You can navigate this tree in different ways. And depending on what's missing, which branch in the tree is missing, you can use other information to fill in those missing values. For example, some of the basic rules. I'm starting out with either it's M or M complement. Either it's a male or not a male. Well, those two probabilities are going to add up to 1, aren't they? Now, in this area of the tree, I'm given that it's M complement. I have the female. Those two probabilities have to add up to 1. Because those are all the options. If I have a female, she's either in state or out of state. So these two probabilities have to add up to 1. And it's likewise up here. If I've selected a male, he is either in state or out of state. So these two probabilities add up to 1. So you could see if in your problem, as you're filling out the tree, suppose you had this number, 6.63, and you didn't have this one, no problem. You can find it. Just basic rules. That has to be 0.37. What about my joint probabilities over here? They have to add up to 1 also, don't they? Because they represent all the 4 possibilities when I combine these two events. That is a probability tree. And I can use it now, for example, to find the marginal probability P of I given M. I'm up here and I want to know what that node in the tree, the probability tree is. Well, I know 0.92 times the unknown is equal to 0.53. Left to right, I multiply. So to get that, I would just divide 0.53 by 0.92 and get 0.58. That's how I find a conditional probability. That's really what we've been doing so far in dividing a marginal, a joint by a marginal. Well, here's another example where if I'm here, suppose I have the conditional and I'd like to know the joint. Well, I know this times this equals this. I get the 0.05. Now those are the advantages of the probability tree. If you can wrap your head around that and understand how to navigate the basic rules, then it's really easy to fill in the missing pieces, isn't it? I think. Any questions so far? Yes.
What does the marginal probability, how would you translate that into like an English sentence? The answer.
The marginals over here, this is the probability of randomly selecting a cadet, and the cadet is a female.
Oh, and never mind, I'm at the last one.
Oh, the joints.
This one.
These are the joints. That means randomly selecting a cadet, and they have both these properties. Both events happen. Female and out of state. Male and out of state.
Okay, thank you.
Okay. All right, let's do one of these together, and then I'm going to hand out a worksheet. And this time we're going to try to solve this problem right from the start using a probability tree. So read the problem. I've got two events. Event A is the person has hypertension. A complement would be you don't have hypertension, high blood pressure. B, the event you have heart disease. B complement, you don't have heart disease. The first thing I want you to do is read the problem. There are probabilities in there. Translate those and put them in the right notation. Okay, take a few minutes. That first sentence is pretty straightforward. In the adult population, 15% have hypertension or high blood pressure. Hypertension is a synonym for high blood pressure. How would I write that as my probability notation? P of what equals what? Hypertension or high blood pressure, it's the same event. I could put hypertension or high blood pressure. Oh. So it's P of A equals 0.15. See some mystified faces. Was that obvious? No? So the second sentence. The study of patients who were previously diagnosed with heart disease found that 88% have high blood pressure. Now that's a little more complicated sentence. How would I translate that into my probabilities? What am I given? Roscoe?
Probability of A given B.
Let's try that out. That would say, I know the person has heart disease. What's the probability they also have hypertension, given that they have heart disease? Studying patients who were previously diagnosed with heart disease. And that fits. That's given. They have heart disease. 88% would also have high blood pressure. Good. That's 0.88. What's the third sentence? What piece of information does that give us? Yeah, Russell?
Probability of B is 12.
Yeah, probability B is 12. So what's the probability of B complement? So one thing you could do is go ahead and create a contingency table. We've done that before, and I did one for you, assuming that you had 100,000 people, nice big number. And those are the values you get for the different cells. I translated those into probabilities just by dividing, normalizing. And I've got my marginals on the outside, and I've got my joint probabilities in the middle. So So let's draw a probability tree, and I'm going to start with A. So I'm going to go with A, then A bar. What's the probability of A? 0.15. And A bar complement, 0.85. What do I do next on the tree? Well, up in this branch, I'm assuming A's already happened. So this is probability of A, probability of A bar. This is the probability of B given A. This is the probability of B bar given A. Do I have those on my table right now? I don't have those, do I? All right, well, let's just fill in what we do know on the tree. The last node here in the tree, this will be the probability of A and B. Do I have that on my chart? Yes. What is it? 0.1056, right? That's the joint probability. Probability of A and B happening together, right there. 0.1056. And this would be the probability of A and not B. Do I have that on my chart? Sure do. What's that? That's let's go ahead with my tree. Down here, now I'm given complement of A bar. What probability goes here? Kowski? No, I have A bar. So probability B given A bar. Down here, the probability of B bar given A bar. I've been given A. Right. Do I know these probabilities from my contingency table? No. You don't know the conditional probabilities from the table, but what do you know? You know the joints. So this is the probability of B bar and A bar. What's that probability? Yeah. A bar and B bar mean I don't have hypertension and I don't have heart disease. 8356. I realize you probably can't read that. That's below the podium, isn't it? And this one would be the probability of A bar and B. A bar and B is 0.0144. So how would I use this to fill in this probability in my tree? Yeah, it would be 0.044 divided by 0.15. So this probability is equal to 0.044 over 0.15. And someone have a calculator? This is equal to 0.1056 over 0.15. Dylan, do you have that?
0.732.
What, this one up here? 0.734. 0.704. Okay. And this marginal probability?
0.2932.
93, something like that. And that's just another way of solving these problems. In this particular problem, the wording of it gave us joints and the marginals, but we could just as well have problems that give us we don't have that. But we could just as well have problems that left different gaps in the probability tree. And you can still fill in the gaps either using that formula or just by basic rules. Okay, any questions? If not, I'm going to hand out a worksheet and you to work here. Yes.
On this, it's multiplying left to right and then dividing right to left,
Yeah,
right?
think of it that way. This times this equals this. Now to get this, the conditional, I divide the joint by the marginal. How would you like the tree method better? Anybody? There's always some that do. Whatever works for you. Okay.